Good afternoon. I would like to welcome you to today's session about aromatic compounds presented by myself, Dr. Ahmed Kamal. Let's first have an overview about aromatic compounds, the different types of aromatic compounds. So we have two types. We have ones that are hydrocarbons, consist only of carbon and hydrogen, like the benzene, the most famous aromatic molecule, toluene and naphthalene. And we have aromatic heterocycles that contain a heteroatom, like the nitrogen, the oxygen, the sulfur, like furan, pyridine, and quinolene. Aromatic compounds, they are famous of having a highly characteristic odor. They all have a characteristic smell, and one of the most famous that's known between people is the vanillin. So let's first start by discussing the parent, the most famous aromatic molecule, which is benzene. So benzene, for the physical properties, it's a colorless liquid. It's highly flammable. Its melting point is 5.5 degrees and its boiling point is 80, which means that at room temperature it's going to be a liquid. It has a sweet smell, and on the bad side it is highly toxic, it is carcinogenic and mutagenic. Okay. The formula for benzene is C6H6, which implies that it is a highly unsaturated molecule. So how is this possible? Because if you have an alkane with 6 number of carbons, its formula is going to be C6H14. And as you know from your previous organic chemistry information, that each double bond is added to the structure, or any cycle added to the structure, will decrease the number of hydrogens by 2. So for example, hexene has the formula of C6H12 because it has one double bond. Cyclohexane also has the formula of C6H12 because it has one cycle. So the structure, so the formula C6H6 implies that benzene is highly unsaturated and it's also cyclic. So what about the chemical properties of benzene? Benzene it has double bonds. So you may suggest that it is like alkenes, but it's not. It's less reactive than alkenes. And one major difference is that alkenes, as you know, undergo something called addition reaction. If you add a reagent XY to the double bond to any alkene, XY like HCl, HBr, Br2 like this, so double bond breaks and 2 positions open to accommodate the X and the Y. This is called addition reaction. However, benzene is not like this. Benzene is not like this. If you add Br2 to the benzene, the addition reaction will not occur. But rather, benzene and the rest of the aromatic molecules undergo substitution. The Br goes instead of the H. It's a reaction called electrophilic aromatic substitution, and it may be discussed in other lessons of this course. So the major difference between and the most chemical property of aromatic molecules and of benzene is that it doesn't undergo addition reaction, and it undergoes instead electrophilic aromatic substitution. Okay, what about the structure of benzene? So many scientists in the past predicted some models for benzene. So for example, Dewar predicted this kind of model, Klaus predicted this kind of model. However, they were proven wrong afterwards by a scientist called Kikuli. So Kikuli suggested that the structure of benzene is a regular hexagon with 3 double bonds, but he also said that the 3 double bonds are not localized, they are delocalized, they move. So he suggested that the benzene is formed of 2 structures that resonate between each other. The double bonds move to give these 2 resonating structures. So there were some arguments against the Kikuli model. The first one is, how did you know this? How did you know that there is resonance? And the second one, why didn't you say that simply the benzene is like the cyclohexatriene? So what made you suggest this model with this structure and the resonance? So the answer is going to be in the next 2 slides. First, the length for the double bond is 134 picometer, while for the single bond it's 147 picometer. So when they measured the bond length for the carbon-carbon bond of benzene, they found that it is 139 picometer, which means that it's something in between the single and the double. So this means that each carbon-carbon in benzene is not single all the time, and it's not double all the time, but it's something in between them. If we return back to the resonance and, for example, talked about this bond is now single. After the resonance, it's converted into a double bond, and then after some time, it's converted into single bond. So it's 50% single, 50% double, which coincides, which goes in agreement with the bond length that was measured for the benzene. So this was the first proof for the Kikuli model. The bond length in the carbon-carbon bond length in benzene is something in between the single and the double, which implies that resonance takes place. The second argument, when some scientists suggested that, why can't you say that the benzene is simply a cyclohexatriene? For this one, they did an experiment which is called measuring the heat of hydrogenation. When you have an alkene and you make an addition reaction, you add hydrogen. This reaction is ectothermic and it produces heat, and you can measure this heat by an experimental technique. So when they measured the heat of hydrogenation for cyclohexene, it was 28.6 kilocal per mole. Okay, when they repeated the experiment for the 1,3-cyclohexadiene, it was expected to be double that amount, and yes, it was nearly double with 54.9 kilocal per mole. When they made the same experiment for benzene, it was expected, the heat of hydrogenation was expected to be triple the amount. So if the structure of benzene is not like what Kikuli suggested, and it is like the cyclohexatriene, it was suggested to produce triple the original amount, 78.9. However, the heat of hydrogenation for benzene was 49.3, which means that the structure of benzene is not like the cyclohexatriene. And also this difference in energy is another proof for the resonance, because the resonance is known to stabilize the structure. So this difference in energy also proves that the three double bonds in benzene are resonating, they are not static, and they are responsible for the stability of this aromatic molecule, which is benzene. So is benzene the only aromatic structure present in nature? Definitely the answer is no. So how are we going to recognize other aromatic structures present in nature? So a scientist called Huckel made something called Huckel's criteria for aromaticity. So for the compound to be aromatic, it has to have these four criteria. First, it has to be cyclic. So let's apply the criteria on the structure of benzene. Let's apply the criteria on the benzene. For the structure to be aromatic, it has to be cyclic. This is the benzene. Benzene is cyclic. Okay, the second point is that for the structure to be aromatic, it has to be fully conjugated. What does it mean, fully conjugated? Fully conjugated means that all the atoms of the cycle have to be sp2 hybridized. Have to be sp2 hybridized. This is what's meant by fully conjugated. sp2 hybridized, in quick words, in quick explanation, meaning that each carbon is connected through to three effective groups. To only three effective groups. If it's connected to four, it's going to be sp3 hybridized. Okay? So here, if we look at the benzene, we will see that each carbon atom is connected to two carbon atoms and a hydrogen, which means that all the carbons of benzene are sp2 hybridized, so the benzene is fully conjugated. The structure has to be planar. Yes, the structure has to be planar because for the double bonds to be made, as you know, the double bonds are formed due to the overlap of the electrons of the p orbitals. So for these double bonds to be formed, the p orbitals have to be parallel to each other. This is the p orbital picture of the benzene. So for effective formation of double bonds, the structure has to be planar for the effective overlap of these electrons in the p orbitals. The structure has to be planar. And the final thing is that the structure should contain 4n plus 2 pi electrons. So what's meant by pi electrons? Pi electrons means electrons present in a p orbital. Or in simpler words, electrons that form the double bond. So what does it mean for n plus 2? N is an integer. We are going to substitute with different numbers and see this number of electrons. So if you add n equals 0, the number of pi electrons is going to be equal to, which means that the structure, if one structure is cyclic, fully conjugated, planar, and it contains 2 pi electrons, it's going to be aromatic. And if you add n equals 1, so number of pi electrons equals 6. This is also aromatic. N equals 2, 4 times 2, 8, plus 2, 10. If a structure has 10 pi electrons, it's going to be also aromatic. So let's count the number of pi electrons on the benzene. How do you count them? Like this: 1, 2, 3, 4, 5, 6. So benzene has 6 pi electrons. So benzene fulfills all the criteria for the structure to be aromatic. Let's look at some of these examples and decide whether they are aromatic or not. So if you find here, for the 1,3,5 cycloheptatriene, it's cyclic, yes. However, this structure is not fully conjugated. Why? Because this carbon is attached to 1, 2, and 2 hydrogens to 4 effective groups. So this means that this carbon is sp3 hybridized. So one carbon of the cycle is sp3, meaning that the structure is not fully conjugated, so the structure is not aromatic. Okay? If you look at this molecule has a top shape. From its shape, yes, it's cyclic. Yes, it may be fully conjugated. All the carbons have sp2 hybridization. However, it's not aromatic. This structure is not aromatic. It's not planar. The structure is not planar, so it's not aromatic because, as you see, it has a top shape and there will be no effective overlap of the p orbitals. So let's now solve these two examples. This structure is directly, you can see that it's not cyclic, so this structure is not aromatic. Okay, let's discuss the final structure, this one, cyclobutadiene. So this structure, is it cyclic? Yes. Is it fully conjugated? All the carbons are sp2 or not, or all the atoms are sp2 or not? Yes. If you see the connections, each carbon is attached to 3 effective atoms, which means that it's fully conjugated. Yes. Is it planar? Yes. It's a planar molecule. However, the number of pi electrons, if we count them, they are going to be 1, 2, 3, 4. There are 4 pi electrons. So what do we call this? This is a new category. This category is going to be called anti-aromatic molecules. Anti-aromatic molecules are highly unstable. We are going to know this further. So you now have 3 categories. Aromatic ones, which fulfill the 4 criteria of Huckel. And you have non-aromatic, which have one of these first three factors not there, not fulfilled. And you have finally the anti-aromatic structures like the cyclobutadiene. It has the first 3 conditions fulfilled, but the number of pi electrons is not fulfilling Huckel's criteria. Okay? This is a summary for what I said. You have aromatic fulfilling all the 4 conditions. You have the anti-aromatic structure. They fulfill the first 3, but they have only 4n pi electrons. They do not fulfill the 4n plus 2 rule. And the non-aromatic structures, in these structures, it's either not cyclic, not planar, or not fully conjugated. So if you know this, we can now be divided into groups of 3 students, and you can now try by yourself. You have like 5 minutes to do it, to solve these structures, and then tell me whether each one of them is aromatic, non-aromatic, or anti-aromatic.